Yeah. Okay. So anyway, we start with relaxations and waves. Okay. Most often when you speak about relaxations, you assume that your graph is finite and it has a sink. In what comes, the main example is actually the whole lattice, let's say square lattice, Z square, and it's infinite and there is no sink. And we still want, however, to have the notion of relaxation. So to start with, this is how we encode the graph. And this horrible slide, we need it only once to define the Laplacian and the top links. So let me go through it quickly. So gamma is the set of vertices of the graph, and it's assumed to be the mostly countable set. So it can be infinite, but mostly countable. And then there is a threshold function, which is something like the degree function, and then there is gamma, which is the function which assigns neighbors to every vertex. And then there are some natural requirements, standard in the field. We assume that there is no loops in this graph, so V doesn't belong to gamma of V, and that there are no errors, or rather, if V is connected to W, then W is connected to V, and the multiplicity of this connection is the same. And finally, the last requirement is that the number of neighbors doesn't exceed the threshold. This is the condition C. Okay. Yeah, as I told, we interpret this tau of E, the threshold, as degree of E, where the difference.
So we require in the axioms that the degree of B, the threshold, is equal to the number of neighbors. No.
No, that's what I'm trying to tell right now, is that in principle those are equal most often. So tau of E and then number of neighbors is the same if the vertex is not connected to the sink. And the excess value, so the difference between tau of E and number of elements in gamma of V, is exactly the number of times your vertex is connected to the sink. All right?
Fantastic.
Let me draw just one example. If you take a single vertex on a square lattice, it's connected 4 times to the sink.
So the sink is kind of an imaginary vertex outside of the lattice?
Yeah, but it's outside of gamma. So gamma is not necessarily lattice. Yes, in our example, it will be always a subset of the square lattice. And the sink is something which fulfills the requirement for this subset of lattice that every vertex has degree 4. So yeah, whenever you have missing neighbors, this means that you are connected to the sink.
So just so to speak, all the boundary, all the ones that are surrounding our graph are the sink.
Yes. Yes, and we never use it explicitly. So in this series of small talks, the sink will essentially, yeah, I think it will never appear in the consideration. It's always there, but it's outside of the set of vertices gamma. All right, so this we need to define the Laplacian. So the Laplacian is defined on the space of functions with values in integers, and the domain is gamma, so the set of vertices, and it's defined in the standard way. So it uses explicitly the threshold.
I have a question here. Why do you use the word multi-set rather than just set? What's the difference between a set and a multi-set?
Well, sometimes you want to have several edges connecting the same pair of vertices. So imagine you have two vertices and they connected twice.
Okay, so the elements of the set could have multiplicity.
Yes. So actually, this is what I added just now, preparing to today. In our paper, it's just set, but quite often you are interested in multi-sets. So, and I thought it doesn't make it worse, but it just serves a greater generality.
So it is the same. This multi-set has finite multiplicities, every element.
Yes, see, because its cardinality is less than threshold.
That's right. So it's the same. What multi-set is what I would have called like divisors, the free abelian group generated by the set or something like that.
Not exactly, because you don't allow negative multiplicities, but yeah.
Monoid, sorry, free abelian monoid
Yeah,
generated by the set.
yeah. Then it's totally like that. Yes. But if you are not comfortable with multi-sets, you can just assume sets, and that would mean that it's just graphs where every pair of vertices is connected at most once.
No, it's perfectly fine. I just wanted to understand terminology. Thank you. It's perfectly fine, multi-set.
Okay, so that's the Laplacian, and next we define a toppling. A toppling is just adding the Laplacian of delta function. That's a weird notation, delta of V. So I've chosen to be consistent with the paper where we write this down, and there it's used in this way, delta of V as a delta set, as a delta function. Anyway, so that's the toppling. Now, a relaxation is a sequence which starts with a given state, phi. And for this series of talks, we, at least for today, we allow our states to take negative values. And that would be necessary for defining the waves. So usually in this sandpile business, states are non-negative integer valued functions on the vertices of your graph. But actually, nothing changes if you allow your function to take also negative values, and it gives even some benefit. So anyway, so a relaxation is a sequence of states such that every consequent state phi k plus 1 is the result of applying a toppling to the previous state phi of k at some vertex where the value is greater than threshold. Okay, so you apply topplings only in the case when the corresponding vertex is unstable, which means that the value is greater or equal to the threshold. So in the case of lattice, this threshold is always 4. So whenever you have 4 or more as a value of your state, you can apply the toppling, which means removing 4 from this vertex and giving 1 to each of the neighbors. And if there is no neighbor, this just goes nowhere. Okay. The toppling function of this.
Misha, can
Yes.
I interrupt you?
Yes.
Well, I just want to say you hi from Yasha.
Oh,
Yasha
hello.
Here. Hello. And from Max.
Here.
Oh, hi.
Hi. And
Hello,
from
everybody.
Natasha. And from Zima. Nihao. Yeah. Sorry for that. I just wanted to add some positive news. Yeah.
I'm very happy to hear.
Thank you. Good.
Okay. Amazing. Okay, I hope we don't cut this from the video. So anyway, so yeah, the doubling function of this particular relaxation is just the sum of delta functions of vertices which participated as the vertices where we did doublings. Okay. So one thing I want to tell you that on the infinite lattice, there are many relaxations which goes forever and never stabilize your state. So, and
So
yeah.
this is this toppling function. It's also sometimes referred to as toppling landscape or something like that, isn't it? It's the number of times that it was.
Also, it's called odometer, and yeah, I don't know. There are many names. But anyway, so what's important is this definition. This relaxation phi with the bullet with the dot bullet. Yeah, it's called locally finite if at every vertex we did at most some finite number of topplings. And then the result of this particular relaxation is phi plus the Laplacian of the toppling function. All right.
Just a quick question. This last statement, the result of this realization is such and such, is a definition. It's not meant in a literal sense, I guess. I mean, because infinite process.
It can be meant in the literal sense. If your relaxation is locally finite, then actually this expression phi plus the Laplacian of the toppling function is the same as pointwise limit of the relaxation sequence.
Okay, but it's an infinite process, and so it's not a finitist relaxation. It's just a limit.
Yeah, but the thing is, for locally finite relaxations, it stabilizes at every vertex. This process can be infinite, but it's finite locally.
So I can imagine just naively that I have the kind of this sequence of compact balls, and I know that at some point, not every compact ball it will stabilize, but it may take longer the bigger the ball.
Yes. So indeed, but there are relaxations which are not locally finite, and the main example is imagine your graph with the lattice, and you take the state which is 3 everywhere except for one point where it's 4, and then if you do the relaxation, you can do as many topplings as you want in any vertex you prefer. So you can do it really forever, even locally.
Yeah, interesting.
Okay, so is the usual definition: a state is called stable if it's less pointwise than the threshold. That's the usual thing, and then a relaxation of usually it's an unstable state. Otherwise, you cannot do relaxations. It's called stabilizing if the result of this relaxation is stable. Okay?
And of course, there's usually many paths to make a state stable.
Yes, there are many ways to do a relaxation in general, but here is a dilemma, very useful one, telling you as a corollary that the results of relaxation, of stabilizing relaxations are always the same. So let's go through it carefully. So if you have a state and a function, so state phi and function f, such that f plus the Laplacian of this function is less than threshold, and it's very important that this function f is non-negative, then any relaxation then any relaxation of this state is locally finite. So it's enough to find one function which probably does a lot of forbidden topplings to assure that any relaxation of this state is locally finite. And as a straightforward corollary, you see that two different stabilizing relaxations must give the same result. And this follows since you can apply this lemma twice. First to use the toppling functions of the first relaxation with respect to the toppling function of the second, and this gives one inequality, and then you can do it interchanging the roles of the first and the second relaxation. So you can. So
Very
since
nice.
yeah, so you have two inequalities. Okay, and therefore we can denote this same toppling function just h phi without referring to a particular relaxation. All right. So one more thing in the same spirit. No, it's not yet there. So a state is called stabilizable, and here I change the terminology. I think relaxable is the wrong term. It should be called stabilizable. If there exists a locally finite stabilizing relaxation. And denote the result of the relaxation. The relaxation is phi circle, and it doesn't depend on a particular relaxation sequence. All right, so that's one of the most important statements from the beginnings of these sandpiles. Namely, if you find this function which stabilizes your state, then your state is
And of course,
stabilizable.
here this function f presumably could make negative some vertices at some point.
Exactly. That's why it's cool. That's why it's very useful. You can do overkill. You can do too much topplings, and still, if you are able to relax, it means that it's relaxable in stabilizable in the honest sense.
And this is kind of a minimax
Yeah.
solution to the PDE or something like that.
Yes. So and then your toppling function is exactly the pointwise minimum of all these functions which make your state stable. Okay, and so this is called the
this is the sandpiles are lazy principle. They are lazy.
This is the least action principle. Yeah. Okay.
Beautiful story, yeah.
So,
but no, is there a criterion given an initial state to know if on the whole plane on this infinite graph to know if such an f will exist?
That's exactly the criterion. If you're able to find some function, then it's stabilizable. You'll see how it's used very, very shortly. We'll use it to define waves, to define to tell that waves at all are well defined for any stable state. That's the preparatory lemma, and that's probably the only thing we'll prove today. So if you have any stable state and you take any vertex and you force the top link. So this is what you don't do during the relaxation. You don't do top links at stable vertices, but here you anyway do it. And what happens is that it results in probably unstable but stabilizable state. Make sense?
It has to be unstable, doesn't it? Because otherwise it would be.
No, it can. It still can be stable. It's like, for example, imagine your state was just zero everywhere, and you do the toppling. Yeah, it's negative at some vertex, and it's one. It's in its neighbors, and it's stable, but it's not a non-negative state. It's not a state in.
Let me
particles.
correct. It's either, if it is stable, it has to be negative somewhere.
It's always negative somewhere. Yes. So because we start with a stable state.
Yeah, of course.
So that's the thing. So unless your vertex is unstable, the toppling applied there makes the value negative. Okay, and so that's the definition. The operator WV of sending a wave from V and acting on the space of stable states is defined by the following equation. So you do the toppling and then you relax the state, you stabilize it. And this definition, it really needs the previous lemma, the lemma above. That it makes sense to draw this circle in the upper index.
What does this look like in action? What does this look like in action?
So imagine you have all threes. And imagine you do a toppling here. Then it gives one here, one here, one here, and one here. But it makes -1 in the middle, where you started. Then you do toppling in every neighbor. And it gives 1 back to the vertex where you started. And so you get 3 again there. And then it propagates. So this really looks like a wave in action. So it starts small and then it
It
goes.
really looks a little bit like if I threw a stone in a pond of water.
It looks like you throw a stone which had a rope attached. In a sense, you throw it and then you remove it. So one way to define a wave is like you add some extra grain, you let the vertex topple, and then you remove this grain you added.
Yeah, I understand. Yeah. Nevertheless, yeah, I understand what you mean by this stone in the, and you remove it, but because the stone is not water, if you just throw the stone in the pond, and the pond is very, very big, what you use is just perturb. What I meant is, you imagine this kind of very flexible surface of a drum, you know? Now you just hit it at the center. Just perturb. So the whole point is you're not adding mass, but somehow you're adding energy.
Exactly. That's
So
very,
mass, but you're adding energy. And so this energy propagates outwards like a wave. So it's a very nice thing that you just defined.
Yeah, that's probably the most useful tool in studying sandpiles, at least in our work. So we try to see every relaxation in terms of waves. Anyway, so let me go through this definition. So what we also define is this H, phi lower index, V upper index. We define it as a toppling function of the relaxation for TV phi. so the top link applied to phi, plus the delta function at v. And we call this the wave top link function, and the wave operator is just adding Laplacian of this wave top link function. Okay, so let's prove the lemma, because it's very easy and you will learn something from it. So the proof goes like this. Observe that the function which is identically 1 on your graph is superharmonic, meaning that the Laplacian of this identical one is non-positive, less than 0. And this is actually equivalent to asking that the threshold is greater than the number of neighbors. This is exactly the same thing. Superharmonicity of the constant function, or constant one. And
you mean harmonic or superharmonic?
Superharmonic. Superharmonic.
Super is less than or equal?
Yeah, less than. I think this is superharmonic. Let me think. Well, I'm always confused about this, so I should have checked, but yeah, I think it's superharmonic. I think, but let me check it for the next time. Anyway, so let's just say that the Laplacian of 1 is less or equal to than 0 if and only if the threshold is greater or equal to the number of neighbors for every vertex. So, and this is what we asked in the definition of our graph. And this implies that if we add to TV of phi 1 minus Laplacian of 1 minus delta v, then it will be less than threshold. Just because applying the top link to phi is the same as adding the Laplacian of the delta function, and that's the one. So meaning that we found a function which stabilizes the top link, the applying the top of the top link function to phi. Does it make sense?
Yeah, a little bit.
So that's very silly, but what we were saying about this least action principle and other things around. So let me just close the door. So what it tells us is that the top link function, the wave top link function, is bounded by 1 essentially. So it takes only zeros and ones as its values.
Yeah.
Okay. And in a sense, this is the smallest meaningful package of top links you can imagine in this sandpile business. And that's exactly how we use it. And this is the last slide for today. If phi is a stable state on the graph and v is a vertex, assume that also that phi plus adding a grain at this vertex is stabilizable, then the result of the relaxation for this state is just applying a bunch of waves and then adding the grain. And you can tell precisely how many waves you need to apply. This is the value of the top link function of the relaxation at V. Okay?
Very nice, very nice, very nice.
So, which means that to understand a relaxation of adding an extra grain to a stable state, you just need to master the waves. And if you,
So
you
are dividing the relaxation. Traditionally, the relaxation would be adding a Laplacian. Traditionally.
Yes.
But now you are, huh?
Yes.
But now you are saying that this Laplacian is the summation of this wave
top link functions. Yes. So
you're decomposing. Is this a sort of position of the Laplacian, or?
yeah. So other way to formulate this would be to tell that the toppling function of this relaxation is the sum of toppling functions of the waves. So there is a formulation where you just say that you do it level by level. So
I understand. Yeah. It's very nice, but yeah, it is some sort, isn't it, of Fourier decomposition of sorts or something, isn't it?
Yes, it's something like that. So okay, the correct statement, I think, is that doing a wave is some kind of infinitesimal. And the relaxation is some kind of integral of waves. So at the tropical level, we'll see, but maybe not next time, but we will see it definitely, that doing a wave is like adding an infinitesimal to a coefficient of a tropical polynomial.
Well, I'd like to understand that better. I'll think about it. Could you send the notes of today here in the chat?
Sure.
Thank you so much.
And
any questions, Daniel?
No, profe, creo que más o menos entendí.
Very well. This was excellent. Thank you, Misha. I will stop recording.